First of all, I would like to thank you very much, the Nensky Institute, for the invitation today, which is an amazing opportunity to me to talk to such a panel of researchers, very intimidating too. And I would also like to point out that I'm not presenting a research today or a behavioral study of any sort. I'm presenting a project that hopefully can become an interesting tool in the hand of bioacousticians. And I'm not a scientist, I'm not a researcher, I'm not a signal analyst, I'm an artist, I am a musician, an architect, a visual artist. I am mostly a musician, but I work as a visual artist since 2008. And this project is very much related to birdsong, but can be also adapted to other kind of animal vocalizations. And I started experimenting with it back in 2017, 18, and it developed over time. So I had other projects in between until last year. I went very much into real-time technologies, especially with Touch Designer, which is an amazing software that can handle data in a very efficient way, is GPU-centric, can be used for a wide variety of purposes in the visual world, including lots of data visualization. And I got this, let's say, this personal idea, this personal intuition to represent sound as points distributed into 3D space over time, creating trajectories. So I started working on these models on Birdsong by intertwining together many audio-driven oscillators, each oscillating to different features of the spectrogram, and creating these point clouds. And then I started to think, well, let's try to add something to this point. Let's try to add some data, some numbers, metadata. So I started calculating simple amplitude for every point, emission time. Then I said, well, let's try to add some more. Let's try to add frequency too. So I started calculating the dominant frequency for every point, using it as color. Then I said, well, let's try to add the spectral centroid. Then let's try to add spectral spread. I started investigating one spectral descriptor after the other, adding a bit more, until I found out myself with a huge list of descriptors. And then I started looking into MFCCs, how they are used in speech recognition, in bioacoustic analysis, and then also chroma later. And I started calculating this set of coefficients, and I wondered, how can I translate these values in 3D space? How can I create a 3D models out of, let's say I have 40 coefficients, I have 3 dimensions, what do I do? So I started looking after the possibilities to reduce high dimensional vectors into 3D space, starting from PCA and then other methods that we will see later. And I started computing these, let's say, analytical models of sound. And I was amazed because the result was very, very similar to the models I began with, my early oscillator, let's say, artistical models. And it was an impression because I realized that by intuition, with just having a vague idea of all the things I went later with lots of research, I went quite close to what can be achieved with formal methods of analysis. And this has been an amazement that stimulated me even more to continue with lots of work and development and to make the project grow to what it is today. Basically, it has become an analytical framework and a visual ecosystem to analyze and classify birdsong in a very visual form. And I can also say that the analytical part has got a much bigger weight than the artistical one. And I'm not even interested in the artistical part anymore, because the analytical one is way more interesting, much richer, and full of potential developments rather than just creating visuals. So this was just to give a very overall idea of how everything started and how it developed. And then I would also like to have a bit of context for the project, because it's worth mentioning, because I do I do work with my own bird recordings mostly. I also did some testing with recordings that I download from Senocanto, but most of the material is my own material. And these are the location where all the birds that you will listen in this presentation have been recorded, which are birds from my own local area. I am a passionate bird lover and bird watcher. I do spend lots of time in nature. And I recorded almost 30 different species here from my area, which is I live in Northwest Italy, south of Turin, in the Cuneo area. There's lots of amazing nature here around, lots of very accessible place where to stay and listen to birds and record them. So, and this is also my gear. I use a Rode condenser microphone for the recordings with an old Panasonic HEX1000, a 4K video camera. And yeah, so to having also a quick rundown on the overview of the process of the workflow, which of course begins with the audio acquisition. That could be field recordings, materials, different kinds of audio sources. And then there is a pre-processing part, which is an important part of the process. We will get into that a bit later. Which is denoising, reverb where necessary, and signal isolation. Then there is the feature extraction and the dimensional mapping, which basically is the extracting acoustic data from the audio and do higher transformation of it. The visual translation, which is the design of the visual models, and then the possible application in the real world. So going to the computational framework of the project, it's done of two main blocks that start from the raw audio, the base audio, and they compute one computes an array of spectral descriptors, which I divided in the Hertz domain, unitless domain, and dB domain. Which go to do different measurements from where the frequency lies where the energy lies on the frequency axis, where shape and dynamics on the spectrum, relative energy patterns and such. And then there is another block, which is the male frequency septural coefficients and constant Q-transform chroma data is computed. And this data in the models as I conceived them now becomes the skeleton of the manifolds, the 3D models, while the descriptors go to create some kind of dressing. Because in the block of the dimensional reductions, we have 4 different methods of reduction in 3D space, which are PCA, ISOMAP, UMAP, and TSNE. And this is what constitutes, yes, the shape of the models, while the descriptors became some kind of dressing that can be varied depending on what one wants to achieve. It can become coloring on the points, point size, it can become metadata, it can become different kind of ribbons, attachment to the ribbons. The visual models can be modulated into many different forms. And also, there are a wealth of possible 2D and 3D graphs that are available that I'm not going to show them today because there's not enough time to do that. And there's also possibility to run with spectral descriptors into the dimensional reduction, but this is something that I into so far, so it's still an unexplored field. So far, I worked with dimensional reduction from the MSCC and chroma data. So here, basically, the manifolds explore 2 different families, 2 different line of analysis for the vocalization and for the sound. One is focused on the timbrical characteristics of the sound through the male frequency septural coefficients, MFCC, which are calculated in 40 coefficients. And another one is focused on a, let's say, quote unquote, more musical analysis of the vocalization based on the chroma data, which usually is very much utilized in music. Is used for pitch detection, chord recognition, and usually is structured in 12 intervals, which corresponds to the 12 tempered semitones of, let's say, Western tonal music. But I increased the number of intervals to 80, and it can go up to 120, which makes more sense in my idea if one wants to try to classify a vocalization in terms of pitch classes, pitch structure. It is necessary to have a much finer grain, a much finer intervals, because animal vocalization doesn't have much to do with music. They have lots of microglide, pitch shifts, and subtle variation and oscillation that cannot fit into a 12 semitone lattice. So what I try to do is to construct a much finer. The calculation is the same, the normalization is the same, just the intervals are much smaller. And I also created a value which I experimented a bit, and you will be able to later in the manifolds, which I called chroma energy concentration, which basically takes the higher energy beam at every sample and applies it accordingly to the model in order to create this sort of energy value that goes up and down depending on what the vocalization does. And you will see that the higher the value is, basically the more the energy is concentrated into a smaller number of beams, rather than when it's more distributed, spread evenly throughout the whole spectrum of beams. And yeah, these are the two data sets that are used to create the manifold. And basically, there are 4 different reduction methods for every data set. So basically, every audio recording creates 8 manifolds. And I also would like to point out that this is quite exploratory work, because first, I don't have the preparation of a bioacoustician. And also, I wasn't able to find anything relatable in the research I did on the internet. I didn't find any material to relate to in this kind of model, so I don't think it's something that has been tried to do before. But I did lots and lots and lots of testing in order to test actually the consistency of the manifolds with many different recordings, also many different audio sources, and many different bird species and many recordings of the same bird to see how the manifolds behave and how they basically they shape in 3D space the values that are computed. And we have 4 different methods, which start with PCA, which basically find the directions of greatest variance. And then there is isomap, that preserve the geodesic manifold distances. It's like trying to unfold a crumpled piece of paper and showing the drawing. Then there is UMAP, which builds a topology based on neighboring points. And TSNE, which is a more cluster-oriented kind of reduction. You will see the difference visually very, very clearly in the examples that I'm going to show you and next. And then there is other picture features that are encoded, as I said, as different kind of visual data in the models that goes from coloring numbers and many other possibilities. And an important requirement for these models is that the audio needs through cleaning. It has to be cleaned very accurately. It doesn't mean that you need say super fancy microphones to record, because you can say my gear is quite entry level, but in that manifolds are quite robust. But the cleaning is important, because anything that happens outside the signal of interest, let's say whatever the noise and recording out in the outside world, anything can happen. But everything that happens that is extraneous to the signal will get into the model. So it will somehow pollute the data. So I always, in the recordings that I have, I always go to very accurate process of cleaning with many denoise passes. And then signal isolation that I do on audio editing software in order to just completely remove whatever happens outside, and possibly also inside the signal where maybe you record birds and there are other birds singing. If possible, they should be cleaned as much as possible. So ideally it should be pristine, but one can do was possible. And also, I would like to have a note on the possibility of interoperability of this framework, which are quite many actually, because do you hear me actually? Is everything okay?
Yes, it's perfect.
Everything is fine.
Oh, okay, perfect. This is a note on the fluidity of the framework, which is quite notable because there's interoperability between CSV data that can come also from other frameworks. Ideally, the math can also come from the values can be computed from other software, other toolkits. There is possibility to add the scripts, other features that won't attach the actual models that I have, because it's so divided in layers, which are very much interoperable, and one can intervene singularly in some preferred point without touching all the rest. And so there is possibility also to plug these models of this framework into other pipelines, other research environments. And there's also possibility to shape much more visual models than what I do so far. It's because they can be retooled and crafted also on data shaped differently from what I did so far. So there can also be, it can also ingest data structured differently in other ways, and different kind of models can be elaborated from that. So the flexibility is high, and there's also transparency in order to exchange data in and out and back and forth. And yeah, so I think that could be an overall presentation of my project. And I would switch to the videos now. I have a number of videos to show you that hopefully will be more interesting than me talking. And also, as a fun note, because before going to the videos, I would like to show you how Birdsong looks on a touch designer network. This is one of the many networks I work on, which are more like city maps than networks. They are quite complicated work in order to make everything properly aligned together and fit properly. And there's a lot of plumbing in the logic too, so it's not easy to put everything together. But anyway, now I will switch to the videos, and I will we interrupt the sharing of the screen because I want to share the player that is there. Do you see a black screen?
Yes, we do.
Okay. Okay, so I will begin with, okay, this videos is here. The first two videos are about the descriptors output. It is just the descriptor. The first is a calibration test, one of many calibration tests that I did in order to test the behavior of the descriptors and how the computed descriptors work. And then the second is a short snippet of a black cap singing with this kind of signal decomposition and the various descriptors.
Should we be hearing any sounds right now?
Are you hearing something?
No, we haven't.
Oh, wait. Oh, wait. I have to share the audio of the computer. That's right. So I will go. How did I do? Don't remember now.
So it's not a matter of the volume.
No, it's that I have to share the audio of the computer. I did it yesterday, but now I don't remember what I did.
So you go to the settings, to the three dots, and you should have the audio.
settings in there?
Yeah, but I'm not seeing it now. What did I do actually?
Maybe the good idea is just to start sharing it once again, because on the sharing screen, on the right side, bottom right side, you got the options to add sound and optimize for the video. Just stop sharing and
yeah. Also, I'll block the sharing. I share it again. And yes, but I cannot see where to share the audio.
You can try with the general Zoom workplace settings. So maybe not really with the with our meeting, but with the general ones. There should be like an audio option.
Yeah, really sorry about that, but
That's okay. We've got time. So
they should be very much into technology, and yet I'm not seeing this.
So maybe those three dots on the right, on the bottom right, and
yeah,
there's the settings, and you
I'm
can
not
try the audio.
having trouble.
Pavel, do you have any idea?
So this is my screen. I see the activate audio, but I don't see any.
Okay, so try to play. Maybe it works.
Is there audio?
No.
Why increase the volume for now? No, nothing.
Not at all. Okay, so I don't layout. I don't see any audio in here.
All right. So
Is...
another thing, are you using the app or?
Yep. Yes, I saw that yesterday, but I cannot find it now.
On the right side and on the bottom, you've got three dots. Called More.
Yeah.
Yes, and there are settings. Yes, so then you put the.
But I don't have any settings now. I have a record.
Adam, can I talk in Italian to him so I can explain better? I'm sorry, but.
Absolutely.
Yes.
Okay. Sure.
Ok, scusami, se apri su altro,
sì?
In basso, riproduci il suono su questo dispositivo.
Non c'è.
Non ce l'hai? Riproduci il suono? Nulla?
No.
Okay, so I don't know what to do. I'm sorry, because I can see it in my computer.
Yeah, I saw that also yesterday, but... oh, wait. I found it. I'm sorry. Now it should work. Sorry. Okay, let's try to see that from the beginning. How's that now?
Perfect.
Okay.
Great.
Sorry about that. So this is a real-time interface I created in order to interact. Okay, this is yeah, this is me talking. This is the longest video. The presentation is 5 minutes long, and we'll talk about yeah, an interface that I designed in order to scroll dataset back and forth and do various things on it. And analyze a specific datasets of bird vocalization. It is done in Touch Designer, and everything is handled visually and in real time. The limit now for this first version is 1 minute worth of audio, but it's going to be expanded in the next version. And all the data is computed in advance via Python modules, and that includes the descriptor array from my models, the MFCC and chroma datasets, and the 8 reduction in 3D space for both chroma and MFCC, which are 4 each. And data can be interacted, manipulated, fine-tuned. There are a number of things that can be done with this interface that we are going to look at now. Here we see a set of panels and geometry view in which can we navigate interactively. So here the network creates a spectrographic image of the sound. Here is a Blackbird recording I did months ago. There is a time window that can go from 0 to 1 minute. It can change in size with the spectral centroid overlaid on it. And there is a cepstrogram and a chromogram, which are the visual renditions of the 40 MFCC from 0 to 39 and the 8 chroma beams from 0 to 79. So now I can try to hit play and see what happens. So I can now here see the model unfold in its real time. I can see how it looks. I can navigate through it. I have coloring from the model applied with spectral centroid, but there are also other descriptors now. I have used also spectral spread, spectral flux, and chroma energy concentration. But it could be basically whatever other descriptor from the array. This is just for demonstration purposes. Also, I'm able to scale the values from the legends that will apply automatically to the models and the graphs. I can fit to the frequency range that I'm interested to, and same applies also for spread. And as well as flux and chroma too. I can scale the upper threshold for chroma, which works like some kind of contrast, and it's possible to see how it becomes some kind of heat map of the harmonic energy at any moment. So you can now switch between the different reductions. Here we have the PCA for MFCC. You can see MFCC isomap, MFCC UMAP. I can scale the models in order to fit them accordingly. MFCC TSNE, and the same goes for chroma. We have chroma PCA, chroma isomap, chroma UMAP, and chroma TSNE. I can change the size of the time window in order to add more data to the model at any moment, or I can reduce it as I wish. I can look at the UMAP now. And there is also possibility to switch to a render view that now I can go full screen here. And I can go to a shaded viewport with a fixed camera, which rotates slowly around the model. I can visually frame it with these two sliders X and Y. I can work on the time window here. I can also scale the points as for my visual needs. Now I go to the centroid as coloring. Also, now the points are, the size of the points is determined by linear amplitude, but it can be whatever other descriptors. And also there is possibility to stop the animation at any moment and export a 3D model of the manifold I'm looking at. It can be exported as an OBJ, as well as a snapshot for every graph here. So I'm thinking this tool as a research instrument for labs, and the idea is to give researchers new ways to look into acoustic data with this instrument that can become maybe a visual complement to the actual methods of research. And you can map descriptors, MFCC, chroma into three-dimensional manifolds that can reveal patterns, correlations, many things that maybe just looking at 2D graphs and spectrograms are not so easy to see immediately. So I hope that it can become some kind of a new analytical lens that can help detect structure of birdsong, compare different individuals, compare species, and do maybe also exploratory work in complex vocalizations. Okay, just a second. Okay, just stop a second just to tell you that now we are going to see outputs created with this interface. And this first video here is a song trash that is computed into an MFCC UMAP manifold, and you will be able to see how the UMAP reduction from the MFCC data creates literally specific basins of 3D shapes where the vocalization go to, and when there is a vocalization which is repeated in almost identical or very analogous form, it overlaps almost perfectly. You will see that also in other versions that I'm going to show you later. But this anyway, this is a song trash. And the coloring is done with a pass of different descriptors that I did. There is not a specific criteria. This is all demonstration work, so it's just to show what the manifold can show and what can be achieved with them. Okay, just let me stop this for a second. Okay, this is a wren, a Eurasian wren that I recorded this spring. And in this recording, he is repeating a set of vocalization very, very similar to them. That is repeating basically the same structure. And you can see how in the UMAP manifold, this structure overlaps almost identically in geometry. It creates very definite geometrical forms. And you can see how it is similar one to each other, but also you can tell, you can spot also the fine differences too. Okay, and now we are going to look at a nightingale song on 4 different manifolds, and you will be able to see how the different reduction works, and you will get a very clear visual idea of them. Okay, and let me stop this for a second. This is a goldfinch, also another MFCC UMAP visualization, and you will be able to see how this vocalization gets, how it is transformed in geometry into space. Also, this one is a very repetitive vocalization. Okay, and then we are going to look at a black cap now in two different manifolds with graphs created from the interface. So we have the chromogram, the substrogram, and the and also the let's say the spectrogram with the spectral centroid on it. Okay, and now there is the last video that I'm going to show you. It's an interaction between two robins that I've been able to record some week ago. And this is a work that I did in a purely tentative way. I mean, it's not a behavioral, it's not a behavioral study. It's just, it want to be a demonstration of what can be achieved working with these models in a proper research environment. And these are shown from MFCC data with a UMAP manifold with shared coordinates for the two vocalization. Basically, the vocalization come from the same recording of the audio. The robins were singing at a few meters apart. I was clearly able to listen to the two of them. And I separated the signal in the audio by looking at the differences in amplitude and reverb time too, which are there were a few, but I don't guarantee 100% on the correctness of the signal separation. It should be correct by most part, but there can be mistakes anyway. Anyway, I did this test in order just to give you an idea of what can be done with proper research. Okay, and do we have still a minute?
If you have something, please go with it.
I would still like to show a video that I made with rodents vocalizations.
Yes, then please show us.
Yes, it is material that I've been provided to by the Nensky Institute, and in order to do some preliminary tests with rodents, and it doesn't have much meaning at all, because basically rodents have anharmonic vocalization that doesn't fit very well with both Sepstrum and Chroma 2, but it's something that I wasn't very much aware of. And anyway, I tried to pass this a set of vocalization into these models by stretching the audio by 10x in order to bring it into audible range. And also because I wanted to kind of in some way listen to how actually rodents vocalize. And I tried to create also 3D models of vocalization, and this is a very tentative preliminary test that doesn't mean much, but anyway, the visual result, you can see it now. So basically here I built a Chroma time plane, which basically is the Chroma dataset, the values in the 80 bins it's showed as raster lines in the graph. There is an amplitude centroid graph, a 2D graph, and the spectral centroid also developing over time. And I recomputed the frequencies. Of course, it's all scaled down by 10x, and it's also slowed down by 10x also. But yeah, this is the visual result. So I think I come back. I'm at the end of my presentation. I hope you enjoyed it. And yeah, basically you can say that this is a project that comes from the art world, from an artist, which is not a scientist, but is somehow pushing into the science field. And it's like I'm trying to throw a ball in the science field with this project, hoping that scientists could pick the ball and continue the game and to pursue direction that I will not be able to do on my own, since I don't have nor the background nor the preparation to do that. But yeah, so this is what this project is about, and I hope you enjoyed it. So thanks a lot.